right, so our final talk of the day, since Helge's talk was rescheduled to tomorrow, is going to begin now. So we are very happy to have Eduardo de Lorenzo Poza, who is at AU Leuven and the Basque Center for Applied Mathematics, and is going to tell us about singularities via arc spaces and Floor homology.
And I should say that you sent the title last time, but due to flight issues and so on, I didn't have time to post it online.
You will have an extended abstract. That's fine. I didn't do my job. I failed to send in the title and abstract, so you're already ahead.
And also, he's on the job market.
Okay, that's very important. Okay.
Okay. So thank you very much for the introduction and everything, and for the opportunity to talk here. So yes, what I'm going to talk about is the content of my thesis. So in some, I wanted to do some introduction, and in some sense, I'm going to combine a bit of what Aline said and what Benjamin said, like about what we want to know about singularities, right? So when we have some singularity, maybe, I mean, there are different contexts in which one has singularity theory. So, for example, one might have a germ, or the germ of a function, or maybe you have an explicit polynomial defining a singularity. And then, classically, the most useful thing to understand the singularities are some numerical invariants. And already in the talks we have had so far, there appeared several numerical invariants, like the log canonical threshold, or the multiplicity, or the Miller number, or Turina number, or I'm sure that every person here has different invariants in mind. And Benjamin talked about categorification, which is trying to lift these invariants to higher structure. So, for example, you could have algebraic invariants. And here you could have related to this, for example, the cohomology of the linear fiber, and perhaps with its monodromy, with the algebraic monodromy, or maybe we have something like the nearby or vanishing cycles, or we could have, well, the derived category, or the Turina algebra. So there are different algebraic environments. And often these are, for example, this cohomology is defined in terms of a geometric object. Which is associated to, which is associated to the singularity. So, for example, we have already talked about the Miller fibration. So since we didn't have the definition in the last talk, I will just do the mandatory thing of stating this theorem by Miller, that if you have an analytic function from Cn to C, then there exists radii delta and epsilon, such that the restriction of f to, well, you take a small disk of radius delta in the domain, and you take its free image, the puncture disk, and you intersect with the ball of radius epsilon, the closed ball, then this is a locally trivial fibration. So here you have this geometric object, like I will just write this, the Miller fibration. And of course, this is the geometric objects can carry structures, and we can ask what kinds of structures on the Miller fiber then inform us about what invariants on the singularity. So, for example, it is a fact that if we take on Cn, so this is a subset of Cn, if we take the standard Liouville form on Cn, and we restricted to the Miller fiber. So I'm denoting by MF. MF is the pre-image of delta, and this is the Miller fiber. If we restrict the standard Leuven form to the Miller fiber, this makes the Miller fiber a Leuven domain. So we don't only have a topological object, we have, for example, a symplectic structure. What other kind of geometric objects are there? Well, what kind of other geometric objects can we associate to singularity? Well, as the title says, I'm going to talk about arc spaces. So I will write that here. Let's write this. So these are the jet or arc spaces. So what are they? When one has a variety, an MJet on the variety is a morphism from spec of C double bracket T modulo T to the n plus 1. So here M is either positive, so M is in let's say natural numbers union infinity. So this we have to think of as an infinitesimal disk, and an arc is a map from here to X. And it is a fact that there is we have the so-called jet spaces J, M, X that have the proper sorry, right here. So what these J, M, X have the property that the points, the C points of this space, so the morphisms from spec C to JMX, are precisely the MJets on X. So these spaces have, so intuitively, if we choose coordinates, this is just giving either if M is infinity power series in its coordinate or truncated power series. For a finite M, if X is, X is a variety, so for finite M, this JMX is again of finite type, but for M infinity, this is like an infinite dimensional variety. So okay, so we have these spaces, and just like the Miller fibration had different structures. So I said like it has the topological or the symplectic structure. These spaces, and in particular the J infinity, the arc space, also have different structures. So we may see them as schemes, but for finite M, let's say, we can consider the analytic topology on that, and then we can also look at their geometric properties. And also for J infinity, we have the motivic measures that allow us to do motivic integration. So that's yet another structure. So usually, I mean, not always, no, but like one constructs the geometric object from the singularity, then starts some algebraic invariant, and from there one gets a number. And a natural question that one might ask is, when can we get the same number via different paths? And in particular, when different structures or different spaces can recover the same numerical invariance. This is often useful because if you have several methods to compute the same number, you can prove different things. So I don't know, in this regard, for example, I just mentioned, okay, sorry. So I didn't mention here that, and this is the other part of the talk, that I mentioned that the Miller fibration has some symplectic structure, and in particular, well, so let me say that if not only do we have that this is a Leuven domain, but there are some technicalities that if So if the singularity of F is isolated, if F has an isolated singularity, then we can choose a representative of the monodromy. So we have, sorry, this is a vibration over the puncture disk. So it has some monodromy, which is well defined up to isotopy. There are different representatives. If F has an isolated singularity, then we can choose the monodromy, which I will denote by 5, to be compactly supported. Which means that it is the identity close to the boundary of the Miller fiber. And furthermore, up to some technicalities, phi can also be chosen to be an exact symplectomorphism. So it respects this symplectic structure of the Miller fibration. And it's a symplectomorphism. Okay. And when we have this, when we have an exact symplectomorphism which is compactly supported, there is a theory called fluoromology that gives us an algebraic invariant. So from the symplectic structure of the Miller fibration, we get other invariant called the fluoromology. And this M is that we can iterate the monodromy, and when we iterate, we get different groups, so we get the plus. The plus. Yeah, there are different versions, so you can have fluoromology, cohomology, plus, minus. So this is some invariant that you can get here. And so as I said, for example, these unexpected results where you recover things you didn't expect. It is a theorem by McKinney that these fluoromology groups recover the log canonical threshold and the multiplicity. Also, you can also recover the log canonical threshold, for example, from the dimensions of jet spaces by work of Mustafa. So we have these kinds of results of, okay, we have, we recover numerical invariants from different places. So to talk about what I want, I need to introduce one final geometric object, which are the so-called contact loci. Okay. And what are they? They are subspaces of these jet spaces. Intuitively, so let me make a picture. So we have, I'm just going to talk in this context. So we have a function from Cn to C, and we look at its zero locus, which will be some singular is the zero locus. And we have the jet spaces of the ambient of Cn. So every point on the ambient is some germ of curve, which we may, okay, so let me write J Cn, comma 0 to be those arcs whose origin, the origin is, you put spec C, you have a natural morphism, and that speaks out the origin of the arc. So these are the M jets in C to the M, whose origin, sorry, whose the origin such that gamma 0 equals 0. And these contact loci that I'm talking about are the subspace of, so the M jets, such that when you substitute the M jet, so the M jet is, as we mentioned in coordinates, is a list of truncated power series. So you can substitute them into our original function F, and we get back another truncated power series in one variable. And what we want this to be t to the m. It is defined mod m plus t to the n plus 1. Okay, so these contact loci are subspaces of Jm, and therefore, as I mentioned, they have an analytic topology, and we can look at their homology and stuff like that. So I want to mention two two of these kinds of results of arriving at the same place in which contact loci appear. So perhaps the most well-known one is the monodromy conjecture, right? Where we have a singularity. We look at the Miller fibration with its topological structure. And from here, as I wrote there, you can have you get the cohomology of the Miller fiber with the monodromy. And from here, this is an endomorphism, so you can look at the eigenvalues. And another thing we can do, as I mentioned, is okay, we have the singularity. We can consider the contact loci. And here we use as I said, there are two ways to look at it. So you can take the arc space and use motivic integration, or you use the topology of contact loci. But the point is, one defines in some way the so-called motivic zeta function, and these are some poles. So these are the paths of, I outlined there, of singularities and geometric construction, algebraic object, and then numerical invariant. And the famous monodromy conjecture predicts that after using some exponential, these numerical invariants are a subset of this. So here we have one place where contact loci appear. I'm going to talk about another one, which is, okay, we need two different paths. So I will use the floor homology I outlined there. So on the one hand, we have the Miller fibration with the symplectic structure. This allows us to define the floor homology groups. And here I have an integer m that is like a free parameter. I can choose different m. And for every m, I can take these homology groups and look at the Euler characteristic. And this, it's a theorem that the Euler characteristic, of okay, sorry. So the Euler characteristic of floor homology is the Lefschetz number of the monodromy integrals. So this is one thing we can do. And another thing we can do is, okay, we take the contact loci again. And now, as I said, they have an analytic topology, so we can consider their compactly supported cohomology. And once again, we can just look at the Euler characteristic. And now we are not in the same situation as in the monodromy conjecture. So, okay, so this is a big open question. This is the monodromy conjecture. Now we are not in this situation because now there is a theorem telling us that these two invariants are the same. Theorem by Deneuve and Lecerf. So now we can play so, I mean, perhaps naively we could ask, okay, we have an equality of Euler characteristics. Does this come from an isomorphism? So this is a question. Does this come from an isomorphism of the homology groups? Okay. And this is with what we call the arc floor conjecture. AFC. Okay. So yes, we have this question. Do you have any question? Yeah.
Sorry, I just want to make sure to say that this would contribute to conjectures of the poles according to our eigenvalues.
That no, well, these are rational numbers and these are roots of unity. So you have to do some exponential, and it's not an equality that every pole gives. Yeah. Okay, so no other question, right? So I guess I yeah.
There a reason why I would have expected the arc flare to be conjecture to be true besides the numerical evidence?
Yes, yes, so I'm getting at that, yes, yes. Okay. So let's see. Well, first of all, I will give you some. So let me tell you what is known about that conjecture right now. So known results. Okay, so perhaps the first result is by Budur, Bobadilla, Leonardo, yeah, which says that for any f, we have that the arc-flare conjecture holds or m equals the multiplicity of f. Okay, so in this lowest, well, actually, so perhaps one relevant thing is that for m smaller than the multiplicity of f, this is just 0. And then m equals multiplicity is the first time this is non-zero. So in that first non-trivial case, we have this equality of the homologies. And I must say, so I'm glossing over one thing. There is a shift here, but I don't remember what the shift is, and I don't think it's relevant for the story. So okay, we have this first result. Then there is a result by De La Bodega and myself, stating that the arc-flare conjecture holds for n equals 2. So this means for plane curves, we have a polynomial in two variables, and then as long as it has an isolated singularity, so the polynomial must be reduced. Then we have for every m an isomorphism, and then another result by myself and Yahweh form that the conjecture, the arc-flare conjecture holds for f semi-homogeneous. Which I will mention. So what is semi-homogeneous? You can just think it's a homogeneous polynomial plus higher order term. So it's that the initial form is homogeneous, and then it has an n and a degree. So this holds for f semi-homogeneous if the degree is either small enough or large enough. Okay. So this is these are the cases in which this conjecture is known. There is even more evidence to think that it's true, but I will get at it. Okay, so I want to.
But so sorry, can I ask again? Besides the evidence for the conjecture,
Yeah.
like, what is there some geometric reason why I would have expected it to be true? Something like Blur cohomology of a,
So
psychomorphism is related to like loops or arcs.
Yeah. So
I mean, I guess Blur cohomology is related to loops. So
yes. So this is more of an idea. So there is. So what? Okay. I was going to say this in the end. So of course, the first thing one should do if you want to prove something like this is to give a map, and then try to say that this map is an isomorphism, right? So as far as I know, there is no proposed map written down, but MacLean has proposed in talks and so on a map. So the idea is that when you have okay, I'm not good with the drawing, but let's say you have here the nearby minor fiber. I don't know. I know that the drawing is sketchy, but the idea is that this flare homology the generators of the complex are fixed points of this iterated monodromy. So they are some point that goes back to itself when you apply the monodromy. And then the idea is that there should be some filling of this loop that passes through the singularity. And this filling, if this iterates m times, intersects this with order of contact m, which is an empty.
So sort of PSS.
So there is this, this is the idea. Yeah. Okay, so I want to talk about each of these three, not each of them, but I want to give some ideas about this. And the key in all three cases is to use a resolution of singularity. So let me say, okay, so why, so suppose, let me say that we have H from X to Cn that minus 1 of 0. Let's say that this is an embedded resolution of singularities. Meaning that the pre-image, so this is a proper birational morphism such that the pre-image of the origin, which is the singular point, is a simple normal crossing divisor, and the pre-image of the total transform of f minus 1 of 0 is also a simple normal crossing divisor. And so if we have such a resolution, we can use it to talk about these two objects that the conjecture talks about. So first of all, we have a campus model for the monodromy. So the idea is the following. I will make a picture in the case of plane curves because it's the easiest. So say you have a resolution and then you have some dual graph of the resolution. This is the best graph I have. And this is the dual graph. Every point is one of the divisors of the irreducible components of the exceptional divisor, and you connect two of them when they intersect. The minor vibration is the vibration of nearby fibers of the singularity. In our resolution, we have replaced our singularity with the exceptional divisor. So the nearby fibers are something that are close to the exceptional divisor. So the campus model, and I will not say too much because I think Helge will talk about this tomorrow. Yeah, yes. Is a construction which allows you to describe the Milnor fiber and the monodromy in terms of these resolution. So what this picture is supposed to represent is close to every divisor, we have an explicit expression for the Milnor fiber. So we have a piece of the Milnor fiber close to this divisor, and we have like formulas for it and for the monodromy. And in the connection of two divisors, we also have a formula. So basically, the Milnor fiber is chopped into pieces, and on every piece, we know both the topology of the Milnor fiber and how the monodromy looks. So we have a decomposition of this kind. So using this, we can control pi to the m. We are lucky, we can compute. So this is what we do for both curves and semi-homogeneous singularities. Using this kind of decomposition, we can compute Floer models. Okay. What about the other side? Here we want to understand the compactly supported cohomology of contact lossing. So what we need is to describe geometrically what these contact loci are. So how do we do this? Well, the idea is that we have, so let me say, we have the resolution here from X to Cn, H, and we are studying arcs here, right? So these are jets in Cn. So let me say that for this to work, we need to go to m equals infinity and look at arcs. So the evaluative criterion for properness and separatedness tells us that there exists a unique lift of this map, which geometrically means that, for example, in a setting like this, when I have an arc through a singularity, it lifts to the resolution, and therefore the origin must pass through some point of the exceptional device. In fact, we work with a specific kind of embedded resolution called M-separating resolution, which means that M-separating means that if we have two different irreducible components, EI and EJ, that intersect, so if this is non-empty, then the sum of their multiplicities, so which I denote MI and J, the sum of their multiplicities has to be strictly greater than M. So this is a numerical condition that you cannot just start with an arbitrary embedded resolution, and you just blow up the if two divisors don't satisfy this, you blow up, and you do this enough times, and you get one of these resolutions, so this exists. And these resolutions have the advantage that now we know that this lifted arc will not meet. So if we have the exceptional divisor like this, a priori it could happen that the lifted arc gamma tilde passes through the intersection of two, but this condition disallows this. So in these kinds of resolutions, this is not possible, and we know that the lifted arc will go through some exceptional device. And this gives us a partition of the contact locus associated to this resolution. So we have the M contact locus. We know that it decomposes as a disjoint union, set theoretical, so this is not a topological disjoint union, into this XMI, where this is the gammas in the M contact locus, such that gamma tilde of 0 is in EI. And this is for all the I. This is a union over all exceptional divisors of the resolution. So we have this kind of decomposition. But as I said, this decomposition is a union, a set theoretical disjoint union. But if you look at the topology, it may well happen that you have one set XMI, and then you have like this X and J. That's just it. So we want to understand when we have this kind of behavior, right? So so why do we want to do this? Because if we identify which I's are the ones that give us irreducible components, each of these has a topology that we can understand more or less from the topology of EI. So this is there's some work, but one can do this. And then we would have a disjoint union, and this cohomology would be a direct sum of the different irreducible components. Okay, so we to use resolutions for contact loci, we need to understand this problem. This is the so-called embedded Nash problem. So said explicitly, the embedded Nash problem tells you, I give you a resolution of singularities, and you have to tell me which of these XMIs are the ones such that its closure is an irreducible component of the contact. Okay. So, any question? So I will tell you what we know about this problem. Okay. So basically, we want to find those divisors, EI. So let's say I'm going to call contact divisors. So this contact divisors are those EI such that XMI bar is an irreducible component of the M contact locus. Yeah, and well, to state what I'm going to say now, one has to switch perspectives, and instead of thinking about divisors, one has to think about the valuation they define, because we want to compare. And now I'm going to say something about different resolutions. So I want to say that the essential divisors are those appearing in every, let's say, M-severity global resolution of X. So since basically the irreducible components of Xm do not depend on a resolution of singularities, we know that we have to have an inclusion like this. So the divisors that we care about are a subset of the ones that appear in every resolution, and inspired by the work of De Fernex and Docampo on the classical Nash problem. This is like an upper bound, and we also give a lower bound, which are the DLT divisors. DLT, so it's like DLT evaluations. These are the divisors that instead of appearing in every resolution, they have to appear in every minimum, like DLT modification. Okay, so this is a result by Budur, Fernández Bobadilla, de la Bodega, myself, Fernández Bobadilla, and Belka. And so this is like it gives like an upper bound and a lower bound for these divisors that we care about. So in the end, what I was saying is we want to understand the cohomology of these guys. So what we are able to do. So now I will talk about the case of curves. So n equals 2. And say what we can do. So basically, the idea is that when we have, so in general, there is a dual complex, but here we just have a dual graph. It's one-dimensional. We have vertices and edges. So we look at what happens when you have two consecutive vertices of evaluation, of between. So we have a piece of the resolution graph which looks like this. Okay. In fact, not even like this. So we are studying for every M. So we have some M that we have fixed, and we want two divisors such that, so this is EI, this is EJ, and we want to have that NI divides M and NJ also divides M. Why do we care about this? Because these are, well, because of two reasons. So in the Floer theory side, the Acampo model of the monodromy tells us that these divisors, the divisors with this property, are precisely the ones which give fixed points when you iterate the monodromy n times. And on the side of contact loci, it happens that the divisors with this property are the ones to which arcs can be. So these are the divisors we care about. So perhaps we have other divisors here in between, but every one of them should have evaluation 2, and we have a chain of divisors like this. Then we look at the model of the minor fiber, and it looks like a bunch of cylinders. So we have like a cylinder, and then different pieces here will give us like different cylinders in between. We have, and perhaps we have a union of these. But the key idea is that this Acampo model tells us exactly how the monodromy looks like here. How phi to the m looks like here. As I said, it leaves this set fixed and this set fixed. So it's the identity there. But in between, it is a trend twist. So this is the key. Here we have yeah. And now, one, of course, I didn't define thermology, but you will have to believe me that, as I said, the generators of thermology of the third complex are fixed points of the monodromy, and what one has to do to compute the differentials is to count third trajectories. So these are some kind of pseudo-holomorphic curves with some boundary properties. And what we care about is these boundary properties. So I will just mention. So we should have a map from the strip. So this is R cross 0, 1. I think usually it's the other way around. Okay, doesn't matter. So the Floer trajectories we want to count are curves of this kind, and they satisfy that this line is mapped somewhere in the Miller fiber, and this line is mapped to the image of the model. So the upshot, I don't want to belabor the point, but like the idea is that this line here should get mapped to some path on the Miller fiber, and this other line should get mapped to the image of the monodromy. So since this is filled in, this gives a homotopy between these two paths. But in this specific case where I said that we take two divisors satisfying this, it's not too hard that these two paths are not homotopic. This then twist is not isotopic to the identity. So in hindsight, we know that these Floer trajectories cannot exist, and therefore the Floer differentials are 0. So we have yes. So, I mean, this allows us to finish the computation. Okay, this is and okay, this is the idea for Floer homology, and for contact loci, we do a trick which allows us to use the same argument. So if you consider an arc, then you can consider it to be a convergent arc, so it gives a small disk, and this will give some path on the Miller fiber. And after twisting with the monodromy, we arrive at a similar situation using the curve selection lemma here in the space of jets. So this is about what I can say about curves. Then, okay, and then let me end by saying that in both of these cases, in the other two cases, what's the key? It's also a resolution of singularities, but this time it appears through spectral sequences. So this is more evidence for the conjecture. There are two spectral sequences. Let me state it here. So there is a spectral sequence by McLean, whose E1 page is, and then I will, this is in terms of the necessary covers of, there is some grading, which I do not get right. But there is a spectral sequence whose first page depends on the homology of the nebulous covers of the DI, and it converges to homology. Well, for I mean there are versions for homology, plus, minus, and there is also by the same authors, these authors. They also give a spectral sequence. So you have exactly the same thing, but with the shift that you expect from the conjecture, and this converges to the cohomology with compact support of the M contact levels. So, in fact, these authors originally conjecture that not only there is an isomorphism between these two groups, but it comes from an isomorphism between the spectral seams. So this is what I meant is that using this, they prove this, and using this, we also prove this other result. I don't know. Maybe that's all I wanted to say. If you have a question.
No, it's just so that second spectral sequence only holds for M equals, so for.
No. It holds in general, but the problem is that you have to control the differentials. So when the key is that when M equals the multiplicity, there is only one divisor with the multiplicity equals M, which is the first exceptional divisor. And then there is just one column in the spectral sequence, and you know that it degenerates. The problem in general, why this does not give the result straight away, is that you have to control the differentials of the spectral sequence. And also, I should mention that this does not require, unless I'm mistaken, the F to be isolated singularity. And here, the only reason this requires F isolated singularity is so that this is defined. So the definition that appears in the literature for Floer homology needs this to be compactly supported. And this is compactly supported only if the singularity is isolated. That's it.